This video is sponsored by PCBWay. Welcome everyone. In this video I'm going to show you my new project, which is a quite useful tool. I have previously showed you a 10-channel voltage logger, and now I'm going to show you a 10-channel temperature logger. And it is working along the same principles as my voltage logger, except that now I have custom-made PCBs which will be used to properly place all the components for my project, and have some extra components as well, so I can make sure that everything is in the, let's say, proper order. And what we will have is that basically we will have a STM32F401 microcontroller that will be sitting here, actually in this orientation. And then we will have 10 connectors here, which will receive 10 NTC probes. I have a bunch of these, as you can see, and I have already tried one. So this will be with this JST connector, and that will fit perfectly into this PCB, as you can see. So we will have proper connections for these NTC thermistor probes. And since we have the NTC probes, that means that they are just simple variable resistors. So you cannot measure their resistance, but you can measure, for example, the voltage drop inside a voltage divider. So what I have here is, if we take a closer look, you can see that next to the connectors everywhere we have a place for an SMD resistor, and they are just 10K resistors. So when they are in series with each of these thermistors, they will have a voltage divider, and then I'm reading the output of that voltage divider with the 10 ADC channels on this microcontroller, and then I will be able to determine the temperature. And then if we take another closer look up here, what I do here is that I selected a reference, a voltage reference chip, and that voltage reference chip will provide 3.3 volts, as you can see, and that will feed the voltage to all of these 10 NTC thermistors. And I checked it carefully that the voltage reference that I'm using is able to feed enough current to all these NTCs simultaneously, even when they are at their maximum temperature, so they are at their minimum resistance, so they kind of get the maximum current flowing through the voltage dividers. Then I will show you in some simulations, and you will see it on my website in the article that I wrote about this circuit, that we will be below the maximum rated current, output current of this thing. So it should work properly. I haven't tried it yet, we will see. Hopefully I will not fail. And on the left side of this board, you can see that, or hopefully you can see, I broke out all the leftover pins, so we can have additional things attached to the microcontroller, and we will need that because actually I will use a display and an SD card slot to make this into a nice instrument, so we will need these pins. There are also a few pins left on the right side, apart from the already occupied ADC pins, so I broke them out here, so they will just have some random jumper pins. And at the bottom I also broke out 3 5-volt pins or connections, 3 ground connections, and 3 3.3 volt connections. So if we want to add additional devices to this board, we can use these GPIO pins on the left side, and we can use these additional, let's call them power pins, which can power those external devices. For example, in our case, it will be a display. And then this is the back of the panel. So all the ADC pins are running here, as you can see. So I chose the second layer as the layer for some of these traces, and some of these traces are the ADC pins, and then of course I poured the leftover area with the ground. So then the vias, for example, from the resistors here, they can run through the board, and they can connect, as you can see it here, for example. This guy here, and all these tiny dots are vias. So they connect the, let's call it, bottom of the voltage divider to the ground. And in this case, the ground is it's the ground plane, which is placed on the other side. And this time I chose red colored PCB because the project is related to temperature. So I decided, okay, temperature can be warm, and that can be indicated by red color. So why not do it? And I even tried to make some graphics. So I drew this thing in Paint, Microsoft Paint, and then just put it on the silk screen layer, and you can see that it turned out pretty nice. So we have a sketch of a thermometer there, which shows or indicates that yeah, this panel is related to temperature measurement. And as usual, this board was provided by the sponsor of this video, PCBWay, and now they are celebrating their 9th anniversary. So head over to their website for more information, where you can participate in different events, win valuable prizes, and get very nice discounts. So follow the link in the description and go to PCBWay's website and enjoy their anniversary celebration together with them. So coming back to this project, I will take one of these PCBs and I will show you how I assemble it, and then we will test it and see if it works properly as we expect. So prepare for some close-up videos. So now the board is done. You could see that I was struggling with the soldering, and the simple reason for that is because I have this syringe, and I don't know if I can make it visible, but that is pretty much dust in there. So this soldering paste dried out, and due to the small amount of components, I did not order a stencil for this board, obviously. So I tried to hand solder everything, and yeah, I succeeded at the end, but now we have not the nicest soldering, but it's good enough, I would say. So you can see that everything is correct here. I just used this as a support and I forgot it, but let's get rid of it. So these are the extra pins, and just for fun I used a green header here, and then the higher voltage here is red, the ground is black, and the 3.3 is yellow, and then we have another yellow for the rest of the GPIO pins. And we have the connectors here, so 10 connectors, and you can see the 10 kilo ohm SMD resistors. And the reason why I picked 10 kilo ohm, because this guy here is also a 10 kilo ohm NTC thermistor. So when it is at 25 degrees Celsius, then the resistance of this thing should be 10 kilo ohm. So then at room temperature, the reading of the output of the voltage divider made by or consisting of this NTC plus that resistor should give half of the supply voltage, which is 3.3 volt divided by 2, so 1.65-ish watts. And then basically that's all. So what I'm going to do now, I have a bunch of cables, I have this display, and I have this guy. So I just wire up most of the things, and we will see if this thing works or not. So I have the board assembled, so I just simply inserted the microcontroller, and here we have the display, and hopefully it's wired up properly. So then we get the USB-C cable. Let's connect it. And let's see if anything shows up on the display. And it does. So now we have these readings because none of these are connected to the thermistor. So let me do that. I will just pick the first channel. So that's the most obvious choice. And it's room temperature, so it works. And let me touch this. 27, yeah. Kind of works. Or even I can do something else. I have this guy, a heat gun, for soldering. So we can go up to like 150-ish degrees. I will not do that, but I will heat this thing up a little bit, just to see that it responds to the temperature change. And it does it very well. So it responds quickly. So let's do an experiment just for the lols. So here we have our little display, and I have 9 more of this NTC here. So let me separate them one by one, and let's connect them to the circuit. So this becomes 6. So now the temperature at the 6th channel should go to room temperature. As you can see, it does that. And then let's connect channel 2. It's there. Channel 7. Channel 3. Channel 8. Channel 4. Channel 9. Channel 5. And finally, channel 10. So I made a 10-channel thermometer temperature logger, which works with NTC thermistors. this guy here. And now the only test that I want to see is, I show it on a separate board. As you can see on this board, I put a test pad here, 3.3 volts, and the ground. So I will just measure the reference voltage, just for curiosity. So this is the voltmeter there. And I tap the ground and the reference. And it's pretty much 3.3 volts. This will not introduce too much error for us. That's 3 or 2 millivolts. And you can see also what I want to prove with this is that the supply voltage doesn't drop significantly, or doesn't drop at all basically, when we connect all the thermistors to the reference voltage chip, which is really nice. So now what I have to do is I have to solder some terminals here for the SD card, and I have to connect it to the board, and I also need to connect a button here because we have a menu where we can stop and start the acquisition. And just to show that the logging also works, I will set that system up. So I will return to you when everything is soldered and the button is connected. So here we have the big mass of cables. I have my SD card. So I just insert it in this module and hope that it will work. I haven't tried it yet. And then here we have the USB-C connection. So let's see if this thing blows up or not. So far so good. And I have also attached a button. I'm just using the button part of this rotary encoder. So that will be our control. And you can see that we are reading all the channels. And here we have a small red square at the bottom right corner, which indicates that the logging is not running. So I press this once, and then we have the menu. And first I explain what you can see here, and probably a closer look would be even better. So start is obvious, stop is obvious, and then we have F, K, C. So F is the Fahrenheit degrees, K is the Kelvin degrees, and C is the Celsius degrees. And under the line of these three columns or three boxes, you can see that the currently active temperature is Celsius. The SD card is detected and mounted because we read SD OK here. So the card will probably work, and log_0 will be the name of the log file. So now how this thing works is that if I press the button for a short period of time, we just navigate to the next menu item. I just show it. So now the stop is highlighted. And for example, now I can show you that I can select, let's say Kelvin, because we are doing science, Kelvin degrees. So I long press release. Now the Kelvin became green, so that indicates the user to us that the Kelvin is activated. And here also we see that Kelvin degrees is the currently selected unit. So I press it once again. Now it's Celsius is the highlighted but not selected. Let's choose that because I'm in Europe. Celsius, and let's stick with this. So I can navigate back to the main screen again. And there we go. We see all the temperatures, and I grab randomly one NTC, bring it here, and just see if we can warm it up. And this is the T4. As you can see, the T4 is getting warmer. So I grab that. So let's go back to the menu. And let me start the logging. So what should happen is that this small square here will turn green, and then we jump back to the main screen. So I press this log, release. So this is green, and now the logging should be running. So I just touch a few other NTCs just so we can have some different temperatures. I don't know which are these because I haven't marked them. But you can see that we started to change T5 and T10. So they will get different temperature readings on the SD card. So let's say that we want to finish this. So I go to the menu and I go to the stop. And when I press the button long here, two things should happen. Logging should be stopped, which will be indicated by a red rectangle here. Now it's green because we are logging the temperature. And the log 0 should change to log_1 because we finished the currently used log file and we will start a new one. So long press, release. This turned red. This turned green because we indicate the user that this has been triggered. And the current file is log_1. So then let's return to the screen, but just for the fun part, let's first activate Fahrenheit degrees. So we have Fahrenheit. And there you go, 80 degrees Fahrenheit, roughly 75. So yeah, it's room temperature. So now my United States viewers can also see what's the temperature in my room, and they can understand it better. I never know what Fahrenheit degrees is in Celsius, so I always have to think. But now you see, this is 25 degrees Celsius, or 293-ish degrees, or 98 degrees, 298 degrees Kelvin. So we covered this part. You can see that now we have this nice little board, and we can turn this board into a nice logger. I will probably make another version of this video just to make an enclosure for this thing, because I think it would look nice if a button and the display would be encapsulated in, for example, in a 3D printed enclosure. So I will design a 3D printable enclosure and publish all the files, so you will also be able to replicate it. But obviously now this project works, and it works good enough. So then one important thing is left, is that we have to head over to my computer, and I will explain what makes this thing work, what is the code. So I will go through the code for this microcontroller line by line, and you will see how the readings are done for the NTC thermistors, how we send the information to the display and to the SD card. And finally, we will look at the file or files saved on the SD card. And just one thing is that obviously I put this together on a breadboard previously, so it's here. One thing, when you put the cables together, be very careful. I managed to destroy one of my SD cards because before using these more solid wires, I was using this type of jumper wires. And when I was logging onto the SD card and everything was running on this breadboard, I accidentally bumped into the cables underneath the display. So then I somehow probably made loose some of the cables, and my SD card is not working anymore. It has some garbage files on it with some random size, and I cannot format it and so on. But yeah, enough talk. Let's go to my computer and let me show you how this code works. So let's look at the code for the logger. Just before starting, we are using this STM32F401 microcontroller, and it can be programmed in two different ways. One is to use the ST-Link dongle, and in that case you just go to Tools and of course select your board from the boards manager, but then from the upload method you select the SWT. Or you can use the USB cable. You have to select then the DFU, and then you take the microcontroller, press down the boot 0 button, keep it pressed, then press and release the reset button and release the boot 0. Sometimes this doesn't work immediately, so you will have to do a few trials. And an easy way to see if it was successful is that you open up your device manager, and in the device manager there should be a new USB device which is called something like STM32 bootloader, and if that pops up when the microcontroller is reset, that also indicates that the microcontroller is in the DFU mode, so you can upload the code from the Arduino IDE to your microcontroller through a USB cable. So that's how it works. And then you don't really need a schematics for it. Regardless of that fact, it is on my website, so go to my website and check it, but you just have to know how to read. If you can read, then you can see that the chip select of the LCD should go to PB12 pin, the master out slave in pin of the LCD should go to PB15, and so on and so on. So yeah, just read what is written in my code. And then we use the Adafruit libraries to deal with the display. We use the SPI to deal with the display and the SD card, and I'm using the SDFET library for the SD card. And again, you just have to read. So these are the different pins for the SD card, for the button, and for the display. So that's what we have here. And then these are some temperature sensor related things. So the supply voltage is supplied by that precision wattage reference, and it's 3.3 watt. Actually, as you could see it was 3.297 or something like that. So if you really want to get meticulous with the numbers, this can be replaced, and we can write this or whatever. But we are not very bad with the precision anyway, so this will make it. The V out is just the output of the voltage divider. In the formula, basically, we have the typical voltage divider formula, and then this is that parameter. And then the RNTC is the thermistor resistance in ohms, and actually that will be the unknown value from our voltage divider, because we know the supply voltage, we know the value of the 10K resistor, and we measure the V out. So from that we can rearrange the equation of the voltage divider and get the RNTC, and from that we will use some formulas to express the temperature, because the temperature is proportional to the resistance. There is some formula which we can use and express everything. And here actually this should be 0, but I used another resistance when I was testing everything on a breadboard. But let's assume that this is exactly 10,000, because we are using a resistor with very tight tolerances. So then this is one of the values in the formula. And then we have to know the B or beta parameter of the thermistor. So that's that. And then we note down the room temperature, which is in Kelvin, because the formula, which is using the voltage and or not the voltage, but the resistance of the NTC thermistor and the beta parameter and some other things, accepts and spits out the values in kelvins. So we will have to use a Kelvin. So here I kept a variable for the Kelvin and another for the Celsius. And then you might know this kind of practice because I used this in another project which was related to this project. So I store these variables first for the pins, and then I put these variables in an array. So when I'm iterating through the array with a for loop, I can reach all these pins very easily. And then I do the same with the channel name. So on the left side of the display, you could see that T1, T2 up to T10, which is like the temperature channels. So it's stored here. And then I have the 10 temperatures stored as float, and they are also stored in an array, so I can iterate through them with a for loop. And then we have two separate SPIs because this display and the SD card module built in the display doesn't really like each other, so they cannot really share the same bus. So here I have to define and use the SPI 2 and 3, and I'm not using the SPI 1 because that port is actually located in the analog pin part of the microcontroller. So either I use all of those analog pins as analog pins, or I use them for SPI, but then I lose 4 channels or 3 because I can put the chip select to any IO pin. So then this will take care of the display, SPI2, and SPI3 will take care of the SD card. And for that I have to also define this config. So this will be passed to the sd.begin later on. And then we continue with some file saving related parameters. So we have the object SD or instance, and then we have to know if the SD card was detected or not. And then I have a number for the file names. It's a simple integer which is incremented whenever the measurement is stopped. So after we have the log_0 as the first file, in the next logging we will have log_1, and after that log_2, and so on. And here you can see how the log file name is created. So we have a text here, and then we have a file name number. And pay attention that you should not exceed 8 characters for the file name if you for some reason start to play around with the file names. That is not really tolerated by this code or this library in general. And then we create this SD file, which is our SD file. That will be the data stored on the SD card. And then we create also the object for the TFT. So then this is just using the Adafruit library and then passing the pin numbers for it, and then the object is done. And then I have a list of colors. They are predefined colors, so each of the channels among these 10 channels will have its own color, but some of the colors will pop up twice. And I just picked those colors here, which are more visible with the white background, so that's why some colors show up twice. And then I have menu related items. So the item counter is basically the serial number of each menu item, so start button, stop button, and so on. And then we have to let the code know if some of the items are highlighted or not. So then this will keep track of that. And then I created this temperature ID variable, and it goes between 1, 2, and 3, and you can see what is what. And I picked Celsius as the default. And then we will use just a single button, or we use a single button, not will, but we have already used it, to navigate and to stop and start the logging and select and unselect items. So the state of the button here will be either 0 or 1, so the button is pressed or not. And then we have to keep track of the time for pressing the button. So then here, if we press the button for short time, that will be 500 milliseconds. And if the button is pressed down for more than 1 second, that will be considered as long press time. And then we keep track of the current and the previous state of the button. So those are stored in these variables. And then we also have to measure the time of the button being pressed or when the button was released. So we can see if the press was short or a long press. So that's what is taken care of here. And then this is just to kind of not fire the polling function several times within a short amount of time, this button time will keep track of the elapsed time. So if it sees that the button was pressed several times in less than 100 milliseconds, it will neglect it. Basically, that's what it will do. Then we have to keep track of the logging. So this variable indicates if we are logging or not. And then I have a timer for the ADC readings. So I have to store the millis in somewhere. So that is this variable. And start and elapsed time is used for the logging. So I want to log the elapsed time in the file, which is stored on the SD card. So I use these two variables for that. And also I want to indicate if there is new data available after I finished all the AD conversions, because I only want to write on the SD card if I have new data to write. So I don't want to, let's say, write in the middle of the conversion. So I only let the SD card writing function to start when there's new data available. Then we are in the setup part of the code. So we start the serial, and I just want to mention that it doesn't matter what number you write here, because this is a USB device, but you have to write something there. So I just kept my typical value. And then here, either you wait for the serial port to become available like this, or you just delay everything. So I just picked this because if I'm using the ST-Link dongle to program the microcontroller, then actually this will fail because the serial will not be available, or at least that's what I noticed. So my screen got stuck because the serial never started, and then my code was stuck in the highlighted part. So the code was not progressing downwards, where later on you will see I start the display. So to avoid that, I'm not waiting to an available serial port, but I just use a delay. And then while I'm connected to the ST-Link dongle instead of the USB port, I can still see the updated display. And then I just indicate that serial is okay. I start the two SPI buses, so one for the LCD, one for the SD. And then another interesting thing here, this is very important, that we have to write this. So this microcontroller has a 12-bit AD converter, but by default it runs at 10 bits. And if you don't use this line, then it will run at 10 bits and your readings will be very funny. And therefore you just have to tell the code that, hey, I want to use the ADC at 12 bits. And this line takes care of that message, basically. Then, just to indicate that the microcontroller is running, I blink the onboard LED, which is located at the PC13 port. So yeah, I just turn the LED on and off a few times, and that is enough. And then I indicate that I'm preparing the SD card and I initialize it. We will see this function later. And then I also start the LCD. I erase the screen, and then I just print out some kind of text. So that's there. And after that, after 2 seconds, I basically erase the previous text and I prepare for the next printing, which is the first page and the temperature values. So first we will print the letters on the left hand side, T1, 2, 3 up to 10, T10, and then on the right side there will be the temperature values. And finally we have a button, and we will define it as an input with the input pull-up resistor, which is like integrated in the microcontroller. And why we do this is because if we have the integrated pull-up resistor activated, then the default state of the pin will be 1, and then we don't need any external parts, we just need a button, and the button one side should be connected to the pin, which is here the PB6, and the other side of the button has to be connected to the ground. So when we press the button, then the GPIO pin becomes 0 instead of 1, and then that will be detected by the code or by the microcontroller that the button was pressed. And then when we release it, then the 0 becomes 1 again because of the internal pull-up resistor. It will be pulled up, so then we know that now the button was released. And then we have the main loop, which contains 4 functions. Update selection, so this will be this will run when the menu was changed, so we press the button. The check button is constantly polling the button, seeing if there was a short or a long press. Then we have the update temperature value, which is reading the AD converter, so it's reading the output of the 10 voltage dividers. And then we have the write to SD card, which, if we allow the logging, will log the data on the SD card. Then we have this function which returns with a floating point value, and it takes one argument, which is the number of the analog channel, which goes from 0 to 9, so the 10 channels. So we have the out temp here, which is the return value that we will, or the function will return with. And what we do here first is that we read the raw bits, which is between 0 to 9095. And then we convert it to voltage, and it's expressed in volts, not millivolts or anything like that. The unit is volts. So the Vout will contain the value of the analog channel in volts. And then we know the rest of the values from our voltage divider. So I rearrange the voltage divider formula and express the resistor, or thermistor to be more precise, express the thermistor's value. And here I put 2 formulas in the code, because in my configuration now the top resistor in the voltage divider is the thermistor, so that is the one closer to the supply voltage. But if you have the other way around for some reason, for example, you are not using my PCB, but you are building your own circuit, but you still want to use my code, then if you build it in the other way, that the fixed resistor is close to the supply, so that's at the top of the voltage divider, then you have to use the other formula because you express for the other resistor. So that's how you calculate the thermistor's value. And then we know this. Then we have an equation which depends on these parameters that we just measured, and the beta parameter of the thermistor, and then it returns with the temperature expressed in Kelvin. And then the code checks which temperature is activated, and based on that we return one of these results. So if Fahrenheit degrees is selected, then we obviously have to convert it. Kelvin is the default, so no conversion is needed. And if we want Celsius, then we just subtract this value from the Kelvin reading, and then we get it in Celsius. And then once one of these cases are completed, then the out temp is returned. So then this function will return that one of these temperature values. Then we want to update the temperature value. So that's here. So if we are on the first page, so item counter is 0 and 1 second passed. This you can modify here to anything. So that will be the update frequency of your reading, plus a little more because it takes time to update the display. So you have to take that into account. So actually the update frequency will be more like 1500 milliseconds or 1.5 second instead of this. Because this is just the period of when we are entering this part, but it's not the period of the returning of the AD conversions. So you have to account for these things as well. So once 1 second passed, we iterate through all the 10 channels. So what I'm doing here, I'm erasing the previous data with this. So I just print the previous data with white, and since the background is white, it will merge with the background. And then I do the reading with the previously introduced function, and on one of the pins, you can see it here in the pop-up window, which is one of these pins I defined in the array. And then I put those values into this float array. You can see the components of it or items of it here. And once that is done, then I put the cursor back to the corresponding place where I should start printing the text. I select one of the colors based on this list that I created in advance. And then finally, this conversion, which was created just here, this conversion is printed to the corresponding place. And then that is done. And I wrote it here as a comment that I know that you can give 2 arguments. So I could use this, for example, or more precisely, if my background is white, then this should be white. And I could really, erase the display very nicely. But I'm not printing fixed lengths of text or numbers. And because of that, if I print a longer text and after that I print a shorter one, the difference between the 2 lengths will stay on the display. And that is explained here. So if I was printing 6589.0 and then I will print 1.3, then actually the difference, which is these 3 characters, will remain on the display. It will not be erased. So actually what I will see on the display will be this number. So instead of that, before printing 1.3, I will reprint this with the background color, and then I print 1.3. So then it will be good and nice. And here I commented out some of these because this was just for debugging purposes. And then once the 10 iteration is done, I reset the timer basically, and then I indicate the code that there is new data available. So then let's see how we can write to the SD card. So these 2 variables have to be true, of course, because we have to have running logging, and we also have to have available data. And then once that is done, we open the file which we previously created and we printed the header in it. And then if the file exists, which it should, then we start printing. And first we print the elapsed time, but the elapsed time will be in float type. But unfortunately this SD library cannot deal with floats, but it's not a problem because we can convert the float into an array of characters. So I create a predefined length of a character array. And then I take this d2strf function, which takes 4 arguments. They are described, what is what. So here you can see it nicely. We take the floating point number here, which is the elapsed time expressed in seconds. This will be the length of the character array. This is the number of decimals for the float. So for example, we will print 10.1, and then we will pass the result of this conversion from this number into the time buffer character. And then a character array. And then this array is just simply printed in the line of the SD card file. And then after this number is printed, we put a comma and a space. So then we can iterate through the 10 channels, and we do the same conversion for each channel, and then we print each channel in the line. And then once that is finished, so the iteration is finished, then at the end of that line we do a line break and close the file. So now we have completed 1 line in the log file, and that's all. And then we change the new data to false, and we will be ready to do a conversion again. And once the conversion is completely done, then obviously this new data will return to true. And then, we can start over with this. So that's that. And then we can see how to initialize the SD card. So let's see that. So here is our config that we did previously. You see it in the pop-up window that this is the one which we made before the setup. And then if this was failed, then this SD card detected becomes false, because obviously there was no SD card detected, or the code could not mount it. But otherwise, if this returns with a positive result, so then the SD card detected can be true. We can also create our output file basically, and then I create a header for it as well at the same time. So if we could mount the SD card, then why not immediately create a file on it? So that's what I do here. I write this header, which is now highlighted, but this should be just 10 and not 19. And I do a line break, so when the previously shown code takes over to write the logging result in it, then it will start in a new line. And then I close the file. And that's that. And then we can see how to print the first page. So I erase the previous content here. And then I print the channel names. So T1, T2 up to T10, like these guys here. And then I go and change this small rectangle at the bottom right corner. So if it's green, then the logging is running, as you can see it in the if condition. And if it's red, then the logging is not running. So this is how we print the first page, which is basically just the logging shown to us. Then let's see how to print the second page. That's a bit more complicated because that is the menu basically. So we have a bit larger text because of the buttons, at least in the beginning. And then we erase the previous place and we start with the start button. So that's the button at the top. So yeah, I just explained this and then I just show the rest. So I put the top left corner of the square, which will be filled in with blue color, is at the x equals 8 and y equals 15 coordinate on the display. And then it will be 112 pixels wide and 26 pixels high. So that this is like the dimensions of the box, and this is the starting coordinates. You can also see it if this pops up again. Yeah, x, y, so that's the top left corner of the box, width, height, and color. And then this is how you deal with it. And then I place the cursor inside the box to these coordinates. You have to like experiment where this should end up. And then I select white color. So I will write with white letters over a blue background. And I just print this text. And then the same goes for the stop. And then I print 3 buttons next to each other, which is F, K, C. You could see this when I showed the things. Fahrenheit, Kelvin, and Celsius. So again, I just select their location and size, and then I just print a letter in the box with white color. And then the same goes for Kelvin, and the same goes for Celsius. And then I create another, let's say, box, which is a bit smaller size. So text size is 1. It's a longer box. And then what we do there is we check what is the temperature ID. So what is the currently active like logging temperature. And then we print the corresponding text in this box that we drew. And then that will be the text I also showed that tells the user which is the currently active logging temperature. And then if we go further down, we create another box which either shows you that the SD card is present and it was mounted, so we can log on it, or if that is not successful, then SD not OK is printed in that box. And finally, if SD card is detected, we also create a file name box. So we know that if we could open the SD card, we can log on it, so we can show the user the file name or one of the file names that is currently active. And basically that's all. And finally, again, since we reprinted the second page, we can indicate the user whether the logging is running, green small square at the bottom right corner, or logging is not running. Then we can see how the selection is updated. So this is when we highlight one of the buttons, so the user can see where we are standing in the menu. So if we previously pressed the button, then we of course navigated in the menu. So this became true. So we can like kind of perform the rest of the things which will be prescribed below. So then we have to check where we are in the menu. So the item counter will tell us whether we are on the first page or we are on the second page, but over a certain button. So if we are navigating to the first page, so case is 0, so we went from the second page to the first, so the item counter became 0, then we have to print the first page, obviously. But if we navigated from the first page to the second page, so case is basically non-zero, then we print the second page, and we also immediately highlight the start button with this. So we create a red background for it and we print it again, because basically that's the first control on the first page. So it makes sense that if we navigate to the second page, we should already interact with one of the controls, and it's just highlighted, so it still needs the user to press the button for a long time over while this is being highlighted. So it's just one step easier. And then if we press the button again, then this case will be fired. So we navigate to the stop button. And since we can only navigate in one direction forward, then we know that we came from the start button, so we have to remove the highlighting. So we color it with blue again, but then we have to highlight the stop button. So then we print the stop button basically again, but with red background color. And then same kind of idea goes with the rest of the buttons. So the 3 is the Fahrenheit, and again we remove the highlighting from the previous button, which was the stop button, and we draw a highlighted Fahrenheit box or button. And then if we have the case number 4, we are on the Kelvin button. So the Fahrenheit box has to be unhighlighted, so we remove the highlighting from it, and instead we highlight the Kelvin. And same for Celsius. Kelvin highlighting has to be removed, and Celsius has to be highlighted. And if we would press the button again, you will see it very soon, then this counter would become 0. So then we would print the first page. So after we perform one of these cases, we have to make this false. So we are not having an active selection anymore. We are waiting for the user to press the button again. So then we don't let the code to perform any of these things again until we press the button again. So then we can check the button. It's actually quite tricky, but in a good way tricky how it works. It's not complicated. So we simply pull the button, as I said. So we read the current state of the button, whether it is 1 or 0. If it's 1, it's not pressed. If it's 0, then it is pressed. So here, with this line, we see if at least 100 milliseconds passed. If there is less than 100 milliseconds between two button presses, we don't take care of it, because that might be because of the bouncing of the button. So we keep like at least 100 milliseconds between two incoming signals. And then we see if the last state was high, so the button was not pressed, and now it is low, so it is pressed, then the button is pressed. So we take this opportunity to look at the clock, basically, which is the current value, the momentary value of the millis function here. And that we put it in the pressed time variable, pass it through it to be more accurate with the expressions. Then otherwise, if the last state was low, so the button was pressed, and right now, or like this part, that's what I mean right now. The current state is high, so the button is released. Then we note down the time for the released time variable. So we pass the millis to this variable. And then, since the button was released, we can calculate the duration of the pressed button. So that is the time difference between the release time and press time. And then, based on the result of this calculation, we can see if it was a short press, then we just increment this item counter. We go until 4, and then we would press the button again at 4. We don't go up to 5, but we go back to 0. So we like navigate in a circle. So then we print, when this will become 0, then we print the main page again, which shows us the temperatures. And then if it was a long press, so the press occurred for more than 1 second, then we check where we are. If we are at the 0 item counter, we are on the main display showing the temperature values, so we don't do anything. But if we are at the case equals 1, we are on the start button. So if the logging was not running, we start the logging. So we make this variable true. We start counting the elapsed time by passing the millis value to the start time. We make the item counter 0, so we can return to the first page, and we have to then reset the counter as well. And then we print the first page and jump out. And otherwise, so if the logging is already running, we don't restart the logging or anything. It could be implemented like a pause and continue, but it's just too much work. You can do it if you want. For me, start and stop is enough. So we don't do anything if the logging is already running. And then if we long press the button on the stop button, then we disable the logging or stop it. We create a new file name number. So we start at 0, so it will become 1. And then we immediately create a new file name. So we combine this text with this file name number, which is then cast into string. And then it's passed to this as the file name. So you see it also in this bubble that the file name will become, for example, log_1. And then we immediately print this on the display according to these parameters. And then, since we are here with the new file, why not do this? So we open that new file, and if the file exists, this is just for making sure, we print a header in it. And then this random header is now the elapsed time in seconds, and then the 10 temperature channels. And then we close the file. And after that, we highlight the stop button just to indicate the user that it was pressed. So it becomes green. So that just, it's different than the red highlighting. So we are not on the item, but we also interacted with the item. And then we replace our small logging indicator at the bottom right corner with the red square. So the logging is not running. And then this is just really simply highlighting the currently activated temperature. So if the Fahrenheit was activated, then its background becomes green. And we also pass this temperature ID equals 1, or we pass the number 1 to the temperature ID. So the code, the rest of the code will know that we have Fahrenheit units. And we also print the text in our corresponding text box. So then the code will know the activated temperature by this ID, and the user will know by reading the display because it's written there as Fahrenheit. And then the same exercise for Kelvin. Highlight the Kelvin box, let the code know that now Kelvin is active, and let the user know by printing some text on the display. Celsius, same. Highlight the Celsius button, let the code know that we have to use Celsius degrees, and then write text on the display, so the user will also know. And then we save the last state as the current state. So the most recently read state of the button becomes the last state. So that's the value that we have to compare with in the next button press. And then we also reset the button time. So this will wait again 100 milliseconds. And after that time is passed, then we allow the code to detect any kind of button presses. And basically this is the end of the code. So yeah, it was a little bit longer code, but it's still manageable, I think. And I think it's relatively easy to understand and copy. I showed you all the lines, so you can copy this while I explain it and type it on your monitor or on your keyboard. Or if you want to copy and paste the code or use this exact file, please consider becoming my supporter on Patreon. I always upload my source codes there, so you can get it from there in exchange for a cup of coffee or something. So please consider visiting my Patreon. Also visit my website, because I put up all the resources on my website. And I also have a project page on PCBWay. So visit that project page, because then you can order the same PCB that I made, and then you can rebuild my project. So also head over to PCBWay's website, and you can get many other things probably from my project. If you are interested in the stuff that I'm doing, I have all my projects there. Or if you already have your own project, then you should head over and use their services. So I hope that this video was useful to you. I hope you learned something, and see you in the next video.